Hello everybody, week 12, session 1. Let's continue chapter 7, entropy. In previous lecture, we discussed the concept of entropy. You learned the Clausius inequality. This inequality is valid for both reversible and irreversible process. For reversible process, this actually term equals to 0. For um, irreversible process, the integral of delta q over t is always lower than 0. It's negative. Um, so you saw that we can calculate the entropy change of a system during a process. Actually, always the delta S equals to the S2 minus S1. For internally reversible process, you can write delta S equals to the integral of delta Q over T. Again, this part is just valid for the internally reversible process. And then we discuss, the concept of delta actually. Entropy. Entropy is actually, heat over temperature, and normally this energy is not available for to do useful work. So then you learn two different methods to calculate the delta S entropy changes for internally reversible isothermal heat transfer process, or for reservoir. You can write the delta S equals to the Q over T naught. And remember, for this actually reservoir, the temperature is constant, so you can simply use this equation. The second method, if the table of properties are available, you can use the table of properties to calculate the delta S. So you can actually use the same method that you already used to calculate the delta H, delta U to find the delta S, for different, states, for compressed liquid, saturated vapor, saturated liquid, saturated vapor mixture, and superheated vapor. Then we discussed the entropy change of system. Again, guys, this equation is valid for internally reversible processes. You can write this equation for the irreversible processes, but you need to add S generation on the right side. So if you add the S generation, then you will see that the delta S of a system equals to the S2 minus S1, and then equals to this term. Keep in your mind that the delta S for the system can be either negative, positive, or 0. However, S generation, which is the combination of the delta S for the system and surrounding, must be positive, equals to 0 or more than 0. It's impossible to have a process with the S generation less than 0. And then we discussed that this is actually, another statement for the second law of thermodynamics. We actually process can occur in the direction with the S generation equals or higher than 0. And then if you remember, this is the total S. From the tables, you have the S per unit mass. And then if you multiply this, entropy per unit mass by mass, you can calculate the total delta S. Now let's go over, some examples. Today, I will go over 2 examples, and then we just discuss, another method to calculate the delta S. So for the first example, you have actually heat transfer, the amount of heat transfer between the 2 reservoirs. We have 2 reservoirs. The first one is, the heat source, and the other one is heat sinks. The temperature for the heat source is 1200 Kelvin, and then for the heat sink is 600 Kelvin, and then the heat transfer between these 2 reservoirs is 100 kilojoule. You are asked to calculate the entropy change of the 2 reservoirs. So the entropy change of these 2 reservoirs is actually the total delta S. You are asked to calculate the total delta S. So please, Espen, you learn 2 different methods to calculate the delta S. I just mentioned it, in my previous slides. So just go over those 2 methods. Which one do you prefer to select, the delta S of this, problem? Please pause this video, spend 2 minutes, and then just select, the best equation to find, the delta S. Okay, so let's just go over, this is the two different methods that you learn, in the previous lecture. So the first one, the second one is valid for the, if you have a table of properties. You don't have any table of properties for this problem. Actually, we have no information for the, flow. But you are dealing with two different, actually two reservoir, and then you can use the first method, for the reservoir. So uh, the first equation, the first method is the best one to calculate the total, actually the delta S, for these systems. So keep in your mind that, so this is the best, actually equation, the available equation to find, the delta S. So in this case, guys, we have two delta S, the delta S one for the, heat source, which is the QH over TH, and then the delta S2 is, the QL over TL, and then the total delta S, which is the, S generation, is the delta S1 plus S2. You remember that, the delta S total equals to the S generation. Please pause this video and spend 2 minutes and then try to calculate the total delta S. Keep in your mind that the total delta S or S generation must be a positive value. It's impossible, to have, this process with the, delta S or total or S generation less than 0. Let's spend 2 minutes, pause this video, and then calculate the delta S total. Okay, before you calculate, the total delta S, keep in your mind that, guys, the QH is Q out, correct, from this, reservoir. So it's a negative value, negative 100 kilojoule. And then the QL is Q in. So this is the positive value, 100 kilojoule. So if you use actually, these values for the QH and QL, and you substitute into this equation, you have the temperature. This temperature must be in Kelvin. They are already, in Kelvin. So you are good. What you need to do, you just need to substitute this QH and QL, into this equation to calculate the total delta S1 and the delta S2, and then eventually the total delta S. So look, guys, based on, this calculation, the delta S is 0.0833 kilojoule per Kelvin, and it's higher than 0. So it's this process is possible. This must be higher and also equals, to 0. So this is the first one. Let's go over the second one. I just share a PDF file, for the this problem. Please open that PDF file, and then we will go over, that problem here. Okay. Yeah, this is the, the PDF file. So look, guys, we have a rigid tank contain 5 kilograms of saturated vapor steam at 100 degrees centigrade, and then the steam is cooled to the ambient temperature of 25 degrees centigrade. So in this problem, guys, we are dealing, with just, tank. So it's a good idea if you just draw, a schematic for this problem. However, because you are dealing, with just one tank, I mean a tank, so you can just ignore this. You can skip, this step, and then you can, skip to the second actual step. I mean, to just complete the following table. I mean, just gather all, available information. So look, guys, here we have two steps. This is the closed system. Keep in your mind that this is a closed system. It's very important. If you want to use the energy balance equation, you need to just use the energy balance equation for closed system. So this is a closed system. This is the first, available information. Now you have two states, state 1, state 2, and then you have some information that are valid, for both state 1 and state 2. I mean, M is 5 kilograms. This is a closed system, and M is constant. Now, please spend 2 minutes, pause this video, and then transfer all available information into this, actually table. Okay, guys. So let's go here. I just already prepared, this table. Look, guys, we know that this is a saturated vapor. M is 5 kilograms. This is the rigid tank. Also, this is a closed system. This is very important. I forgot to add it here. So this is closed system. And then the state 2 temperature is 25 degrees centigrade. And then this is a rigid tank. So it's a rigid tank closed system, meaning that the volume is constant and then nu is constant. So the new one equals to the new 2. This is all available information. So for the first part, you are asked to sketch the process with respect to the saturation line on a TNU diagram. So if you want to plot the TNU diagram, guys, you need to have the temperature for both these two, states. You need to have the specific volume and also pressure. The temperatures are available. So you know that the new one equals to the new 2. So you need to find the new 1. And then the last thing is that you need to find both pressure, to pressure, for this, process, for these two estates. So as the, part A for this step 2, you need to find P1, P2, and nu 2. Please pause this video, spend 3 minutes, and then find P1, P2, and nu 2. Keep in your mind that you are dealing with the, estimate. Okay, so uh, for the estate one, what you need to do, you need to use the table A4 saturated water temperature table because you have the temperature. So for estate one, temperature is now 100, and then we have saturated vapor. So what you need to do, you need to report the all thermophysical properties for saturated vapor. For example, you can report the nu G, you can report the SG, all these properties, and then keep in your mind that the pressure is 101.42 kilo pascal. So this is all information. You have the new U, S, entropy, and pressure P1. So for the second state, for state 2, we have the temperature. Temperature is known. The temperature is 25 degrees centigrade. And then, look, guys, we know that the new one equals to the new 2. New 2 is 1.67. And here, the new F is less than 1. And then new G is less than new 1. So, meaning that the new 2 is actually between the new F and new G. So, the second state is saturated vapor, saturated liquid. Correct. So the pressure for this state equals to the P sat. So the pressure is uh, 3.1698. So this is a typo, guys. Sorry, I just copy paste from this one. So the P2 is actually 3.1698, but not this one. So yeah, now you have all available information, guys. You can simply plot the T new diagram. So this is the general actually uh, sketch for the T new diagram. And then what happened, that the first state is saturated vapor. So this is the state 1, and then we move at constant volume. So or constant nu, we actually move in this direction, and then that the temperature decreases. The second temperature is 25, so we move downward. So this is the second state, correct? So you saw that the pressure for the first state is 101.4 kilopascal, and then the pressure for the second state is 3.17 kilopascal. So yeah, this is the T new diagram, the first actually, estate. For the second actually, part, let's see, you asked to determine the entropy change of the estate. What is the entropy change of the estate? You asked to find the delta S for the estate. So for this part, let's go to this. So you sketch the TNU diagram. The first thing is that you need to find the equation. What is the right equation to find the delta S for the S thing? Please spend 2 minutes. Keep in your mind that we just have two methods. You learn two methods to calculate the delta S. So just go over those two methods and then select, the right equation to calculate the delta S for this problem. Okay. So yeah, this is the two different methods that you learn to calculate the delta S. So here we don't have any, reservoir, but the table of properties are available, for the S thing. So this method, the second one, is the best one to find the delta S for this process. So to find the delta S, you can write the delta S equals to the S2 minus S1. You need to find S2 and S1, correct? In the actually previous slides, you found the S1, correct? For the this is saturated vapor, so you can report the SG. So to calculate the S2, you saw that the S2 is saturated vapor, saturated liquid, correct? So because the nu is between, the nu F and nu G. So what you can do, you can write the S2 equals to the SF plus XSFG. Please pause this video, spend 2 minutes, and then calculate the S2 and then substitute into this equation to find the delta S. Okay, so yeah, here you can see that, first you need to calculate the x. Look guys, S2 is equals to SF plus x SFG. So you need to find x quality, and you can find quality by using the nu F and nu G, because the nu 2, nu F and nu G are available. So from here, by using the nu 2, nu F and nu FG, x is 0.3856. Now you have the x, you can write S2 equals to the SF plus x times SFG. You have the SFG, SF in this table, and then you can simply find the S2. So this is the S2. Now you have the S2, you have the S1, you can simply calculate the delta S. So from here, the delta S for the esteem is negative 33.36. Question, please spend 2 minutes. What do you think about this results? Does it make sense to have a negative value for the delta S for the esteem? Please pause this video. Just spend 2 minutes. Think, what do you think, guys, about this delta S? Is it valid? It's not valid. What do you think? Okay, guys, we already discussed the delta S for a system can be either negative, positive, or equals to 0. So this actually, results, this result is valid. Keep in your mind that, guys, S generation, which is a combination of the delta, actually the total delta S must be, positive or equals to 0. So yeah, the delta S for any, for the system can be either negative, positive, or equals to 0. So this actually, results are valid. For the second part, for the third part, actually, you asked to find the entropy change, the total delta S, for esteem and surrounding. So for part three, you need to find the delta S, actually the total delta S. And then you saw that the total delta S is, a combination of the S delta S for the system and surrounding. And actually the total delta S is the S generation. Let's go over, let's select this, video here. Sorry, this PDF file. So the first thing is that to calculate the total delta S, you need to have the equation. So the total delta S is actually S generation, which is the combination for the delta S of esteem and surrounding. You already determined the delta S for the esteem, correct? In the previous, section. What you need to do, you need to find the delta S for surroundings. Please spend 2 minutes, pause this video, and then calculate the delta S for surrounding, and then substitute into this equation to calculate the S generation. Keep in your mind that the S generation must be, positive, must be equals or higher than 0. Pause this video and then calculate the delta S total. Okay, guys, so to calculate the total The delta S for surrounding. We can assume that, guys, the surrounding is a, heat sink. It's a reservoir. And then we can use this equation to find, the delta S for the surrounding. It's a Q into the surrounding over T for the surrounding. So the temperature for the surrounding is available, correct? So it's actually, and then what you need to do, you need to calculate the Q in. So to find the Q in, guys, you can actually calculate the Q out, from the rigid tank. If you write the energy balance for the rigid tank, we can write E dot E in minus E out equals to the delta E for the, system. So for the rigid tank, we have actually, the E dot out, or, Q. So if you just use this equation, you can calculate the Q for, system, for the, tank. And then keep in your mind that the Q into the surrounding equals to the negative Q rejected from the, tank. So if you just use this equation, simplify this equation, write it, the energy balance, for a closed system, you can just simplify the Q. Now you have the Q rejected. If you substitute into this equation, you can find the delta S for surrounding. And then this is the delta S for the surrounding. And then the total delta S is higher than 0. And then you can see that, the S generation is actually positive value. Okay, so yeah, this is the second equation, second problem. Now let's go over, property diagrams involving in entropy. So look, guys, you learned that, for internally reversible processes, we can write delta S equals to the integral of delta Q over T. Or in the differential form, we can write the delta Q for internally reversible process equals to the T ds. Or you can write the Q, if you just get integral, from this, equation, you can write the delta Q for the the Q for the internally reversible process equals to the integral of T ds. This equation means that if you have the TS diagram for internally reversible process, the area under actually TS diagram equals to the Q. Correct? This is really important. So if you have the TS diagram, the area under the TS curve equals to the Q for internally reversible processes. Again, this area equals the Q for the internally reversible processes. Remember, guys, you already learned, for in chapter, I think, 3 or 4, the area under the P nu diagram equals to the, W boundary. So here you just learn that, the area under the TS diagram equals to the Q for internally reversible processes. So you can just write it, based on the unit mass, and then, you can calculate the Q actually, for Q per unit mass, for internally reversible processes. So if we have a constant temperature, what happened? This will be a constant actually, line, correct? And then you can simply write that the Q for the internally reversible, because the temperature is constant, you can write T constant times delta S. Question: what happened? What is the heat transfer for isentropic process? Please pause this video. Just, think 2 minutes. What do you think? What's the, heat transfer for isentropic processes? So for isentropic process, guys, the T, actually the S is constant, correct? This is the definition of isentropic process. Isentropic processes are processes, with constant entropy. So meaning that if you plot the TS diagram, you just move, vertically, for example, from this point to this point, correct? And the area under this curve or this line is 0, meaning that, the heat transfer is 0 for the isentropic process. And this is actually the definition, for the isentropic process. If you remember in my previous lecture, I think the last slide, I just explained that isentropic process are processes with constant S1 equals to the S2. And then these processes actually have two main, specification. The first one is that they are internally reversible, and the second one is that they are, adiabatic processes. And here you can see that, actually they are adiabatic, process, because, when S is constant, the area under the TS diagram is 0. So, yeah, the area on the TS curve represent the heat transfer rate for internal reversible processes. The second, actually, a diagram is the Muller diagram. Muller diagram, guys, is the diagram for the H, versus S. So, if you have adiabatic steady flow devices, adiabatic steady flow devices. Look, there are two main actually specification: adiabatic and steady flow devices. If you have the Muller diagram, guys, the vertical distance for the delta H between point 1 and point 2, assume that you have the HS diagram and then you move from the point 1 to point 2. So for adiabatic steady flow devices, this vertical distance actually represent the net work per unit mass. Why? Let's write, the energy balance, for this steady flow, devices from chapter 5, correct? So if we have a steady flow, adiabatic process, the Q is 0, then, we can cancel, velocities and G's, and, Z, the elevation difference, and then you can simply write the W net equals to the m dot H2 minus H1, or per unit mass, you can divide both sides by the m dot, and then you can write W, this is not W, yeah, W equals to the H2 minus actually H1. So, yeah, and then this horizontal distance is actually delta S, for this process. So if you have the Muller diagrams, H versus S, and then you move from point 1 to point 2, you can simply calculate the delta H and the delta S. And the actually, and then the delta H equals to the, work per unit mass, and then the delta S is a measure of irreversibilities. So, you have an HS diagram in figure in appendix A10. Please check the appendix A10. Here you have the appendix A10, and then you can simply, if you have the Muller diagram, you can simply find the work per unit mass from the Muller diagram. The TS relation. This is the last part of, my today lecture. Okay, question, guys. You have argon, and then you have a piston cylinder device, and then initially, that the volume, specific volume, temperature, and also you have the specific volume and temperature for the final state. You asked to find the entropy change of the argon during this process. Please spend 2 minutes, guys, and then try to find the delta S for this system. Keep in your mind that you already learned two methods to calculate the total delta S, actually the delta S. The for the reservoir, and also if you have, the table of properties. Please spend 2 minutes and then find, the delta S. Pause this video and then find the delta S. Okay, guys. Probably you couldn't find, any table for the argon. This is, normal. And then the conclusion is that, guys, we need to have another method to calculate the delta S, correct? You just have, table of properties for few, substances. So we need to just learn actually to develop some new methods to calculate, the the delta S, for, different, substances. So what is the third method? You can actually use the TS relations. What is the TS relation, guys? Assume that we have a, closed stationary system, and then you can write, the differential format of, energy balance. So for a stationary system, the delta E for the dE for the system, which is combination of U kinetic energy and potential energy, can cancel kinetic energy and potential energy. Keep it just, this is for the, internally reversible process. For internally reversible process in the previous, actually, slides, you learned that, you can write the delta Q equals to the TdS, correct? What is the delta W? The delta W you already learned equals the P d nu. If you combine, these three equations, you can write TdS minus P d nu equals to the du. Or if you bring the P d nu to the right side, you can write the TdS equals to the du plus P d nu. This is actually, or if you can just write it, based on the unit mass, if you divide, both sides, by the end. This is called the first TS equation, or the Gibbs equation. So if you just divide, the both side of this equation by T, you can just write it based on the DS. You can write the DS equals the du over T plus P d nu over T. What is the importance of this, equation? You can calculate the delta S by having, information for the delta U, pressure, temperature, and the delta nu, correct? And you have actually, tables, you have, different methods to calculate the delta U, pressure, d nus, and then by using this correlation, you will be able to calculate the ds. This is the first, Gibbs equation. What is the second Gibbs equation? The second Gibbs equation, you can start from the definition for the enthalpy. If you remember, enthalpy is U plus P nu. So if you just get, if you write this actually, differential form of this equation, you can write dH equals the du plus P d nu plus nu dP, correct? This equation. Now let's compare, this equation with this one. If you compare this equation with this one, you can see that, the du plus P d nu, these two terms here, equals to the TdS, correct? So if you substitute for this actually, two terms from the first Gibbs equation, you can write the dH equals to the TdS plus nu dP. Or you can write it based on the TdS. You can write the TdS equals the dH minus nu dP. This is called the second TdS equation or Gibbs equation. And then you can just write it based on the ds if you just divide both sides, by the temperature. This is the second, actually Gibbs equation, correct? So what happened? You just found, two differential equation or two TdS diagram. These are very important because by using these two equations, you are able to find the delta S for, substances if you have no actually tables of properties. How? So to calculate, you actually use, these two equations. You actually need to get integral to calculate the delta S. So you need to have a relationship between du and temperature and d nu and, temperature, correct? And you already learned actually d nu p and t. You already learned, this equation in chapter I think 3 and 4. You learned that the du equals to the cv dt, correct? You learn, also you learn, the dH equals to the Cp dt, correct? So you have a relationship between dH and temperature. You have a relationship between du and temperature. What's about the second term, into these equations? So you already learned, some relationship between P nu and T. You learn, the equations of state. You can use the equations of state, to just substitute into this equation, to solve, these two differential equations. So you have enough information to solve, these two differential equations. So keep in your mind that in the previous slide, I wrote, the those actually I started from, the internal reversible, equation. But these two equations, the Gibbs equations, are valid for both reversible and irreversible processes. So you can use these two equations for both reversible and irreversible processes. Also, you can just write these two equations for both closed and open systems. So now you know three different methods to calculate, the delta S. The first one, for the reservoir, you can write delta S equals the Q over T Not. The second one, table of properties. If you have the table of properties, just use the table of properties. Delta S equals to the M times S2 minus S1. Then the third one, by using the Gibbs equation. How? We will discuss it, in the next lecture. How we can use these correlations to calculate the delta S. So please study example 7.1 through 7.5, and thank you very much. Have a great day.